So how does the exchange of data and control frames in particular time happen? So before sending a frame, the source station senses the medium by checking the energy level at carrier frequency. So a channel uses a persistent strategy with back off until the channel is idle. After the station is found to be idle, the station waits for a period of uh, DIFS. Then the station sends a control frame called request to send. So when it requests to send, after receiving the request to send, the uh, waiting a period of time of short interframe space, the destination sends the control frame called CTS clear to send to the source station. This control frame indicates the destination station is ready to receive the data. So now the data is sent. So this CTS clear to send, which is being sent by the destination, is not only received by the source but also by other stations, which starts its NAV. And this acknowledgement which the destination sends saying that the data is received properly is also being received by other stations, which ends the NAV for other stations. So this acknowledgement is needed in this protocol because the station does not have any means to check for the successful arrival of its data at the destination. On the other hand, the lack of collision in CSMA-CD is a kind of indication to the source that the data have arrived. So this is how the exchange of data and control frames happen in time. So what about collision during handshaking which happens? So what happens if there is a collision during the time of RTS or CTS control frames or in transition? They are often called as the transition, the handshaking period. So two or more stations may try to send a RTS frame at the same time. Maybe A is sending to B and C is also sending to B and so on. So that may cause collision. These control frames may collide. However, because there is no mechanism for collision detection, the sender assumes there has been a collision if it has not received a CTS frame from the receiver. So if both of them send at the same time, then they will wait for CTS and the collision would have occurred with both the RTS at station B. So none of them will receive CTS. The backup strategy is employed and the sender tries again sending the RTS. So that is how it works. We discussed something about hidden station problem in the last video. The solution to the hidden station problem is the use of handshake frames RTS and CTS. So figure shows that RTS message from B reaches A but not C. So however, both B and C are within the range of A. So the CTS message, which contains the duration of data transmission from B to A, reaches C also. So the station C knows that some hidden station is using the channel and refrains from transmitting until the duration is over. So the hidden station problem is solved there. And the next sub layer is going to be point coordination function. So the point coordination function is an optimal access method that can be implemented in an infrastructure network, not in an ad hoc network. It is implemented on top of the DCF and is used mostly for time sensitive transmission. So PCF has a centralized contention free polling access method. The access point performs polling for stations that are capable of being polled. The stations are polled one after another, sending any data they have to the access point, like a time sharing mode. So, example of the repetition interval. To give priority to PCF over DCF, another interframe space, that is PIFS, has been defined. So PCF interframe space is shorter than DIFS. This means that if at the same time a station wants to use only DCF and an access point wants to use PCF, the access point has the priority. So here access point is there and PIFS, and we have the that is SIFS over here, and after that the polling happens. So polling checks whether the station has some data to transmit. So on receiving the polling at the polled stations, this after a short interframe space, the acknowledgement plus data is being transmitted, and based on reception of that one, the short interframe space, the acknowledgement and polling are being considered, and it goes on until the contention frame end. So after that contention free transmission ending, there comes the contention space where the other stations after NAV is over can search for the carrier, sense for the carrier free. So this beacon frame is going to denote the starting of any transmission. So due to the priority of PCF over DCF, the stations that only use DCF may not gain access to the medium. So to prevent this, a repetition interval has been designed to cover both contention-free PCF and contention-based DCF traffic. The repetition interval, which is repeated continuously, so repetition interval which repeats continuously again and again, starts with a special control frame called beacon frame B. So when the stations hear the beacon frame, they start their NAV. So when the beacon frame is identified, other stations start their NAV for the duration of contention free period of the repetition interval. So that's what I told you in the last slide. So during the repetition interval, the PC point controller can send a poll frame, receive data, send an acknowledgement, receive an acknowledgement, or do any combination of this. And this 802.11 uses piggybacking, getting acknowledgement, right? At the end of the contention free period, the PC sends a CF ending contention free end frame to allow the contention based stations to use the medium further. So this repetition interval repeats. Now, what about fragmentation? The wireless environment is very noisy, so frames are often corrupted. A corrupt frame has to be retransmitted anyway. So the protocol therefore recommends fragmentation, the division of a large frame into smaller ones, so that in case there is some corruption, that corruption happens in a smaller frame, so that that alone can be retransmitted instead of retransmitting the whole frame, the whole larger frame. It is more efficient to reset a small frame than larger one.